The problem is this process takes on the order of 10 or maybe 100 years in order for us to get enough of the sugar broken down. That's why we need an enzyme molecule, and the enzyme in our body is called sucrase. Sucrase breaks down sucrose. It catalyzes that reaction, so it happens very quickly. And the key is, and here's a ball and stick shape of what sucrose looks like, it needs to fit exactly into that active site. When it does, it can bind into the enzyme. The enzyme then can then catalyze the hydrolysis, or the breaking apart of those two individual monomers into its separate pieces. And then it lets go of the glucose and the fructose, and we get our enzyme back again, and something else can bind into that active site. So this is one very simple example of why molecular shape is very important. A lot of times you're thinking about small molecules interacting with proteins or interacting with other molecules, and you want to think about the shape of that molecule to think about how that interaction is going to take place. So what we're going to use to think about molecular shape or molecular geometry is what's called valence shell electron repulsion, or VSEPR theory. And this theory is very convenient for us to be thinking about because we are now masters of drawing Lewis structures, and VSEPR theory is based on Lewis structures, and also the principle that when we have valence electron pairs, they're going to repel each other. This makes sense. Anytime you have negatively charged electrons, you want to get them as far away from each other as possible because they're all negatively charged. And the other principle is that the geometry around that central atom, which you've identified as the central atom in the Lewis structure, is going to be such that it minimizes the repulsion between those either bonding electrons or the electron pairs. So when we talk about VSEPR, there's a special nomenclature that we do use. And in VSEPR, we have A. Does anyone know what A means in VSEPR theory? It's the central atom. What about X? So this is actually the bonding, any bonding atom you call X. And then we have E, which is equal to lone pairs. So E is a lone pair. E is not a lone pair electron, so if you have two electrons, that's one lone pair. All right, so there's some guidelines that we use when we're coming up with these VSEPR geometries. The first thing we talk about is the steric number, which we use to predict what that geometry will be. When we're talking about steric number, all we're talking about is adding together the number we have of bonded atoms plus the number of lone pairs. So essentially, we're just adding X to E, and that gives us our steric number. So for example, if we look at this molecule, which is AX2E, what is the steric number here? Yeah, it's 3. So we have a steric number of 3. Something that I want to point out is that we could have a different molecule, which is also AX2E, but in this case, we have a double bond between the central atom and one of the X atoms here. And what I want to point out is in VSEPR theory, we treat bonds as bonds. We don't worry about if they're single or they're double or they're triple. So again, we call this AX2E. This again has a steric number of 3. So what's important in terms of VSEPR theory is the number of atoms bonded to a central atom. What's not important is the types of bonds that we're dealing with. A few other guidelines I want to mention is, first of all, to think about resonance structures. So on Friday, we were talking about the chromate anion, and we said that here are 2 of its resonance structures here, but that we could actually draw 4 more resonance structures. And I just want to point out, when you take a molecule that has many different resonance structures, and you want to draw its VSEPR, its Lewis structure, and its VSEPR geometry, you can take any single one of those resonance structures. It doesn't matter. You'll all end up with the same geometry.